UT, which is called Koopman operator, we can link properties of this operator to dynamical properties of T. For example, and I don't want to say too much about what some of these terms mean. Certainly you'll be introduced to them throughout the week, and some of the operator algebra stuff I will come back to later. So for example, T is ergodic if and only if we have an eigenvalue of 1 with multiplicity 1. It's weakly mixing if 1 is the only eigenvalue. And it's mixing if this limit exists. And I think this is called spectral decay. It's not totally a spectral thing, but again, it's totally written in terms of the operator, which is very nice. This also allowed von Neumann, after Koopman had introduced his operator, to introduce new invariants for measure-preserving transformations, like the spectral type, spectral multiplicity function. And so this is maybe one of the places where we really see things that are really known in operator theory and operator algebras being used directly in dynamics as, invariants and things like this. Okay, but we're here to talk about operator algebras, not just single operators. So the operator itself obviously stores quite a bit of information, but it's still rather coarse. So let's look at an entire algebra. Now, for a function in L infinity, we can represent this on the L2 space just by multiplication operators. And then we can look at the weak operator closure or strong operator closure. I think it's the same in the end, but I did tell you von Neumann algebras were strong operator closed, and I thought I corrected that. But anyway, it's the same. So you take the von Neumann algebra generated by these multiplication operators and the Koopman operator. And this gives us a von Neumann algebra, which we denote by L infinity cross Z. And then the question becomes how much of the dynamical information is remembered by the von Neumann algebra itself. Okay, so we heard a lot about group actions earlier. And this is really where it's even more useful to consider the entire von Neumann algebra rather than just a single operator. So if we take a countable discrete group, then again, for every S and gamma, we have a unitary operator on the L2 space of gamma now. And we already saw this earlier again. This is just going to be the left regular representation. And if we have a probability measure preserving action of gamma now on a measure space, then for every S, we also have the corresponding Koopman operator, which is unitary in L2x mu, on L2x mu rather. So we can construct what's called the group measure space. So we take the Hilbert space, which we get by taking the tensor product of L2x mu and the L2 space of gamma. And we're going to represent both L infinity x mu and gamma as bounded operators on this Hilbert space. So we're just going to map F to its multiplication operator tensor, the identity, and then we're going to map S and gamma to this should be a capital U, the Koopman operator tensor, this left regular multiplication operator. And then if we let FUS denote the image of the multiplication of these two operators here, we can look at the von Neumann algebra closure of these operators where we index, where everything's all functions in L infinity x mu and all S in gamma. And we denote this in this cross product like way, L infinity x mu cross gamma. So this group measure space thing already appeared in the early papers of von Neumann and Murray. So it goes way, way, way back, right to the beginnings of operator algebras. And it's still, these things are still very much studied today. So we could look at this in terms of commutation relations between these functions. And what these are doing is encoding the action inside the algebra as an inner automorphism. So if we conjugate a function in L infinity x mu, thinking of it as sitting inside this cross product, by the corresponding unitary operator of S here, then we're just going to precompose with alpha S inverse. Maybe alpha S. It was late. I'm not sure. But anyway, both work, thankfully, because these are indeed invertible. And when it matters, I'll try to be more consistent. Okay. Okay, so we want to do the same game that we did with the single operator and now try to reframe some of the dynamics in terms of the operator algebra. So again, we're going to have a countable discrete group acting on a probability measure space with a probability measure preserving action. And we see that, for example, the action is ergodic and essentially free if and only if this von Neumann algebra is a factor. So that just means it has a trivial center. These are sort of like the building blocks, the simple guys in von Neumann theory. The action is amenable, which now we know a reasonable amount about. So here's another equivalent definition, actually, of an amenable action, and that's if this von Neumann algebra is hyperfinite. So hyperfinite means that it is the closure of an increasing sequence of matrix algebras. So you map one matrix algebra into another, blah, 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 take the closure, and you get something that's called hyperfinite. And for example, if gamma is ICC, you get a type 2-1 factor. And again, I don't want to say too much about what these mean. They might pop up elsewhere in other people's talks. The real take-home message here is that actually this remembers quite a lot about what's going on with the group and or the group action. Okay, so recall the notion of orbit equivalence, or if you haven't seen it before, we can define it this way. So if we have two probability measure preserving actions, then we can define orbit equivalence via these equivalence relations that we learned about this morning. So this is exactly what we saw earlier. So our alpha is just going to be pairs x1, x2, where x2 and x1 lie in the same orbit of the group action. And similarly, our beta. And then we say that these guys are orbit equivalent if there is a map phi x to y, which maps equivalence classes to equivalence classes almost everywhere with respect to the measure on y. And this group measure space construction preserves orbit equivalence. So you really can think about this sort of construction as an actual invariant, which tells you that it's invariant with respect to orbit equivalence. But what's really more remarkable is that this actually goes both ways. So we actually get isomorphism of our von Neumann algebras if and only if these guys are orbit equivalent. So these von Neumann algebras perfectly capture orbit equivalence of these group actions, which again is really quite nice because this means that you have a lot of algebra tools you can use that you maybe don't have access to otherwise. Maybe. Don't think so with the von Neumann case. Okay, perhaps you need to preserve the L infinity part. Yeah. Okay. Yeah. Right. Yeah. Sure. Yeah. To get the map that sends x to y. Yeah. Sorry about that. All right. So if we have a countable discrete amenable group and the action is ergodic and essentially free, then what we saw from the other slides, putting that all together, we get a hyperfinite 2-1 factor as this cross product. And Alan Kahn showed that there is a unique hyperfinite 2-1 factor. And in fact, this means that all such actions are going to be orbit equivalent. And for this, he got the Fields Medal in Warsaw in, I guess, 1983 or something like that. And in fact, one really doesn't need group actions at all, just the corresponding Borel equivalence relations, which were introduced again this morning. So we can actually construct a von Neumann algebra directly from a Borel equivalence relation on a measure space without, it doesn't need to have a group action involved. Later on, when I talk about C-star algebras, which I'm much more familiar with than von Neumann algebras, you'll see some version of this, essentially. And then Kohn, Feldman, Weiss showed that every amenable equivalence relation on a standard Borel space is hyperfinite. And hyperfinite here is essentially the equivalence relation version of what we saw for von Neumann algebras. It just means that there's an increasing union of finite equivalence relations that give you the countable one. So the upshot is that ergodic theory and the theory of von Neumann algebras, in particular Kohn's classification of factors, is really intimately linked. And they have been since operator algebras really came into existence. All right, if we want to move now from ergodic theory to topological dynamics, we have to move from von Neumann algebras to C-star algebras. And C-star algebras are really going to be more of the focus of this talk, so I'm glad that we might learn about von Neumann algebras in the amenable course a little bit. So C-star algebras are really more my thing. So what exactly is a C-star algebra? Well, we saw that they were originally introduced by Gelfand and Naimark as these subalgebras of bounded operators on Hilbert space, but they also have the following definition. So you take a Banach algebra A, this is a normed complete algebra. You take a conjugate linear involution, and you want the Banach algebra norm to be a C-star norm. So a C-star norm means that it has to satisfy the C-star equality here, which means that whenever we take A star A and take the norm, it's the same as taking the norm of A squared. So if you were to equip just a regular if you were talking about Banach star algebras, you would only have a less than or equals to here. But here we actually demand equality. And this makes C-star algebras significantly more tractable than arbitrary Banach algebras or Banach star algebras even. And there's a lot of magic that sort of happens because of this norm, which we will see perhaps tomorrow. But I will mention maybe a few things where this appears also today. Okay, so examples that you should keep in mind are matrix algebras over the complex numbers. And the involution is the obvious thing. We're just going to take the adjoint and we're going to use the operator norm, and versions of an operator norm are going to come up over and over again. I guess I've already mentioned it in terms of bounded operators on Hilbert space. So more generally, of course, you take any Hilbert space, doesn't need to be finite dimensional, and you can look at the bounded operators on that. That is, again, going to be a nice C-star algebra. And any normed closed self-adjoint, norm closed, not normed closed, norm closed self-adjoint subalgebra, which is the thing that we saw Gelfand and Naimark talk about. These are called concrete C-star algebras because they're concretely represented on a Hilbert space. Another very important example to keep in mind are continuous functions on some locally compact Hausdorff space. The involution is just going to be pointwise conjugation, and for the norm, we take the supremum norm. And this is a very nice C-star algebra. Unlike these two here, it is actually commutative, whereas these are highly non-commutative. And somehow these are like the two extremes of what can happen in C-star world. So here is the map of C-starlandia. And on one coast, we have the sea of topology. And on the other coast, we have this sea of linear algebra. And most C-star algebras, of course, will live in here somewhere. And it's very useful when you're thinking of C-star algebras to pull intuition from both sides. So a lot of times we'll see that they act very topologically, and a lot of times we'll see that they'll act a lot just like matrices, which everyone knows and loves, which is one of the reasons C-star algebras are so great. Okay, So one of the most important and celebrated results in C-star algebra theory is the Gelfand-Naimark theorem. So let me introduce star homomorphisms. These are exactly what you think they should be. They're going to be algebra homomorphisms between our C-star algebra that preserve the adjoint. Notice that I don't ask that it's continuous. So this is a priori just an algebra homomorphism, but the C-star norm implies that these are always going to be norm decreasing and hence continuous. So this is one of the really nice examples of the C-star magic we get from the norm, our C-star norm. We don't need to ask for continuity. It's automatic, which means that in some ways these behave, you can really just consider the algebraic properties, which is really nice. Okay, so Gelfand and Naimark showed that if we have a commutative C-star algebra, then there always exists a locally compact Hausdorff space X such that as a C-star algebra, A is isomorphic to C naught of X, which we saw on the previous slide. And A is unital if and only if X is compact, in which case we just write C of X without the 0. And if we have compact Hausdorff spaces, X and Y, and a continuous map between them, we always induce a star homomorphism from C of Y to C of X, given by precomposition with the map phi, and vice versa. So any star homomorphism between commutative C-star algebras will also give you a map of the underlying spaces X and Y. So this is why we think of this as non-commutative topology. So we have a duality between these two categories, the category of compact Hausdorff spaces with continuous maps, and the category of unital commutative C-star algebras with star homomorphisms. So you'll often hear C-star algebras referred to as non-commutative topology. By contrast, a commutative von Neumann algebra, which again is an example of a C-star algebra, is always of the form L infinity X mu for some measure space. So we can think of von Neumann algebras as being something like non-commutative measure theory. And passing from von Neumann algebra theory down to C-star algebra theory is a lot like passing from what you know in ergodic theory down to topological dynamics. So a lot of the similar difficulties pop up. And just like maybe when you're moving from ergodic theory to dynamics, you take a lot of ideas from the ergodic theory where things kind of work better and then you need to tweak them a bit for the topological setting. This is something that very often happens in C-star algebra theory because the von Neumann stuff is older and tends to be more well-developed. Okay, so the point is that we would like now to look for an analogous relationship between topological dynamics and C-star algebras to that we've seen from ergodic theory and von Neumann algebras. And again, this is a very popular direction of research. I'm sure we'll hear talks about it throughout this week and the rest of the semester. Okay, so a concrete C-star algebra, as I mentioned, is a norm-closed star subalgebra of some bounded operators on Hilbert space. And these are what appeared in the original paper of Gelfand and Naimark. A representation of a C-star algebra is basically allowing one to represent A as bounded operators in some Hilbert space, meaning that you can see that A will be isomorphic to, well, if this map happens to be injective, then you get that A is isomorphic to a concrete C-star algebra. So you might ask, can we always do this? And the answer is yes. So every C-star algebra is isomorphic to an operator norm closed self-adjoint subalgebra B of H for some Hilbert space. And the way this is done is precisely by saying every C-star algebra admits a faithful representation, which means this map here is injective. So in fact, these abstract C-star algebras defined via this norm condition turn out to be precisely the same as concrete C-star algebras. And using representations is something, again, you see throughout the theory. It's a key way of building C-star algebras from other mathematical structures. So the idea is you encode your structure somehow as a star algebra, and then you want to find a map from the star algebra into some Hilbert space. And if it's a nice continuous map, then you can look at the closure of this inside the Hilbert space. This is a C-star algebra. And now we get a C-star algebraist toolkit, which allows us to study whatever original structure, which of course in this case will mostly be coming from dynamical systems. And in particular, it gives us access to C-star algebraic invariance. So the idea is we get a topological dynamical system. We want to construct a C-star algebra. We want to study properties of the C-star algebra. And whenever possible, we want to relate those properties back to the dynamical system, and vice versa, if possible. So what kind of properties might we look for in a C-star algebra? Well, some obvious questions when you're given a C-star algebra are to ask things like, is it unital? What is its ideal structure? In particular, is it simple? And in the C-star framework, what we mean when we say ideal with nothing else is always a norm-closed, two-sided ideal that's moreover self-adjoint. Is A finite dimensional? Is it infinite dimensional? Is it commutative? So we might know which of these coasts in C-starlandia is the most appropriate way to study it from. Can we approximate A bitractable sub-C-star algebras? So by this, I usually mean something like an inductive limit. Can we find a nice inductive sequence where these ANs are much more tractable than our original A? For example, one common thing to look at is if you can do this with finite dimensional C-star algebras, which is akin, again, to this hyperfiniteness in von Neumann algebra theory. And if we can break it down into these smaller parts, maybe we have a better chance about saying something about A itself. And another question, which is really somehow in the spirit of something like amenability, which we'll hear a lot about, is does it have good finite dimensional approximations? And so this is a bit of a vague statement. Let's look into that a little bit more. So what could I possibly mean by finite dimensional approximations? In the case of von Neumann algebras, we had this notion of hyperfiniteness, which meant that a von Neumann algebra is the closure of an increasing sequence of matrix algebras. So we could just do the exact same thing in C-star algebra world, take a bunch of matrix algebras with maps between them, and take the norm, a norm closure, take this inductive sequence. What do we get? We get something called uniformly hyperfinite algebras. So this is an autocorrect problem that keeps happening, and it's extremely annoying. I try to fix it over and over, and it just keeps putting back to hyperfine, which I don't even think is a word anyway. So I don't know. Okay, so we get these UHF algebras. Somehow in spirit, they're very close to hyperfinite von Neumann algebras, but they're actually a comparatively small class of C-star algebras. Very nice C-star algebras. Very nice C-star algebras, but still relatively small. Okay, we can get a little bit more if instead of just saying, let's take matrix algebras, we can take inductive limits of finite dimensional C-star algebras. Finite dimensional C-star algebras are always just finite direct sums of matrices. So this is allowing for slightly more general finite algebras in our sequence. And of course, this will contain the UHF algebras, but it's a strictly larger class. And these are called approximately finite C-star algebras, or AF C-star algebras for short. Both of these are perfectly reasonable generalizations of hyperfine von Neumann algebras. Again, that should be hyperfinite. But we can even go a little further. So I should just maybe say that these two constructions, if you sort of did them in the von Neumann algebra setting, would give you the same thing. They would just give you hyperfinite von Neumann algebras. So it's not clear immediately which is the better pick for an analog. And in fact, we even have more possibilities. We have things called nuclear C-star algebras. So a C-star algebra A is nuclear if and only if it has the completely a positive approximation property, which means that the identity map can be approximated through finite dimensional C-star algebras. Maybe I could just write down a picture here because I think I have more time than I thought. Is there a... Thank you. I'm freed from being behind the computer for one moment. Yay. Yeah, I can... All right. So what this is saying in a bit more of a precise way is that a C-star algebra A has the completely positive approximation property if the following holds. So for every finite subset of the C-star algebra, I'm going to use these double inclusions to mean finite. And every epsilon greater than 0, there exists a finite dimensional C-star algebra or you could also just ask for matrices that would work as well. And completely positive contractive maps. I'll say what these are in a second. So you want one of these maps going from A to F, and you want one of them going from, oh, I used F twice. That's no good. Let's call this B. B back to A. And you want this to approximate the identity map in the sense that, such that if we take psi composed with phi and apply it to A minus A, this is less than epsilon for every A and F. And so the picture one usually draws is that you have the identity map. And this is something, oh, this is B again. This is like a commutative diagram up to F epsilon. So whereas before we had we were asking for actual subalgebras, finite dimensional subalgebras. Now we don't quite have that because completely positive maps are not quite star homomorphisms. They're reasonably well behaved, but they're not multiplicative. So completely positive, we saw the notion of a positive map before. Basically, this means in this context that, okay, so a map between C-star algebras is positive if phi of A star A equals, well, let's say is in B star B. These are positive elements in a C-star algebra. If you talk about something like a commutative C-star algebra, these are exactly functions that'll only take positive values. If you think about matrices, then these are going to be guys with positive real spectrum that are self-adjoint. But I'll just use this shorthand we'll talk more about that later. So it's positive if this holds, and it's completely positive if its amplification to matrix algebras is positive. This is something we do a lot in C-star algebra theory, is consider matrices with entries in the C-star algebra. This turns out to again be a C-star algebra. And we want that the amplification is also positive. So if phi n is positive for all n. So any star homomorphism is completely positive, but these are strictly greater class of maps. We saw things like these conditional expectations. If you have a conditional expectation between C-star algebras, then it's going to be, we're going to ask that it's completely positive, etc. If you were to replace these with star homomorphisms, you would get exactly AF-ness. Okay, how do I turn this back down? So this is another, the CPAP is somehow another weakening. So we went from UHF algebras to AF algebras. Now we're weakening things a little further. And we can sort of think of this as admitting non-commutative partitions of unity. So in particular, if we do start off with a commutative C-star algebra, so this should not say A is a locally compact Hausdorff space, it should say A is C of X for a locally compact Hausdorff space, then A is nuclear, and the way you show this is exactly by just constructing partitions of unity. So these partitions of unity are what give you the completely positive maps. You're sort of taking functions that are continuous and approximating them by sort of like little liney guys using the partition of unity. And I really want to stress that nuclearity is in some sense an immutability type condition. Yeah, as I mentioned, there's still far more general than AF algebras, and there's still a reasonable analog of hyperfinite von Neumann algebras. Okay, so we had this list before of things we might want to look at if we were presented with a C-star algebra. And so I just want to add to this list, we want to ask, is A nuclear? Okay, so we can sort of sweep UHF-ness and AF-ness into this guy. And this is somehow a property that will hold in much greater generality. And I guess I'm supposed to take a break at some point, so maybe I should do that now. We are out in the woods, maybe here, and you come across one. You want to know if it's dangerous or not. So yeah, we'll add nuclear to the list. This turns out to be quite an important property. Okay. So what kind of C-star algebra we actually decide to construct depends a bit on what dynamical information we want to capture. In this talk, I will mainly stick to a very similar construction to the von Neumann one, but hopefully if I have time in later lectures, we'll see different constructions with the purpose of capturing different information. We'll talk a bit about Smale spaces and their C-star algebras. But for now, we'll just start with this analog of the group measure space construction. Again, so we're going to now have an action of a countable discrete group on a compact Hausdorff space now. You could do this with locally compact, but I automatically end up writing compact anyway. So to avoid outrageous typos other than hyperfine, we're going to assume compact. Things tend to work a little bit better there. Anyway, so by Gelfand duality, we know that we have an action of gamma now on C of X, given in the obvious way. So we're just going to compose with this alpha of S to any function. And just as before, C of X and gamma will both act on Hilbert space, and Hilbert space is the L2 space. And we can again look at the C-star algebra generated by operators on this Hilbert space tensor product. Once again, we have faithful representations. So if we just map pi again to multiplication operators, tensor the identity, and we can again look at this left regular representation, tensor this unitary. This gives us these satisfy the following covariance conditions. So in B of H, if we conjugate by these unitaries any image of a function, then this is the same as first applying alpha s to the function and then applying pi. So again, these are really going to be implementing the action in this Hilbert space. But in C-star algebra world, this is not the only pair of faithful representations that will satisfy this covariance condition. When we have such a pair, we call them a covariant representation of the group action. So we don't know necessarily what to do. We could take any pair of faithful representations and ask that they satisfy this covariant representation, and then look at the C-star algebra that's generated by the images of these maps, which I'll denote by C-star rho mu. And this seems like just as good a definition for a cross product as, or for a group measure space type C-star algebra as any other one. So this obviously raises the question of whether the choice of these representation matters, or maybe we always get the same C-star algebra as long as we choose faithful ones satisfying these covariant conditions. But the answer is it can actually make a difference. So this is something that, again, presents more difficulties in C-star algebra world that we don't necessarily see in von Neumann algebra world. However, there's always a smallest such C-star algebra and a largest C-star algebra, which we call the reduced and the full. And the smallest is precisely the one that's generated by this representation that we saw in the previous slide. So this is the left regular representation, more or less. And well, it is, I guess, the way I defined it. And this is just C of x acting on L2 by multiplication operators. So what do I mean by this? Essentially, they have a similar dense star algebra, but their completions are different. Their C-star norms are different. So the C-star norm of the full is going to be larger than the C-star norm of the reduced. Essentially, this is coming from considering all covariant representations and taking a supremum. Of course, to do that, you need to know that there's some bound on such things. That turns out to be true. So this makes sense. But yeah, this is something you see actually quite often in C-star algebra world, that if you have a star algebra or something and you want to complete it, there might be more than one way. So we denote the reduced with this little r and the full with this little f. Sorry about that arrow. Can I move the arrow? I cannot move the arrow. All right. Oh yeah, okay, oops. All right. Right, so these are the ones that you normally see studied. Of course, in particular, the reduced group C-star algebra, cross-product C-star algebra. But it's also an interesting question to see what other guys there might be in between these two, or whether these are the only two. So we're already seeing that this is seeming much more complicated than our quick look at ergodic theory / von Neumann algebras. However, if the action is amenable, then it turns out that these two cross products coincide. So they're isomorphic. And hence all cross products, since they lie between these two, coincide. So we really can think of there being a single cross product in the amenable setting. So we just drop the R or the F here. And we just denote it as the cross product. I mean topologically amenable, yes, which I didn't actually define. Okay. Yeah, perhaps I should have done that. But I just really want to highlight that topological dynamic properties get reflected in the C-star algebra. That's really the takeaway here. I don't want to bog people down in definitions today. So the natural question then is that, does topological amenability imply an analog of hyperfiniteness, like we saw happening in the von Neumann setting? And what analog should we expect? Which of these three, UHF, AF, nuclearity? And the answer is yes. And in fact, this action is amenable if and only if this cross product is nuclear. So this is why one of the reasons why I wanted to say that nuclearity was really sort of amenability type condition for C-star algebras. And in fact, if you know anything about topological amenability, you know that you get these like Fulner set type things, and these are sort of finite dimensional type objects in your group, and these are exactly what you use to construct these things to show nuclearity. So these are very, very similar notions in this particular setting. Oops, this doesn't work. That's the point. Okay. Okay, so we have a nice analog of some other things, such as we saw that if we have an ergodically essentially free action, then we get a factor. The analog in the C-star setting is a simple C-star algebra. So it has no non-trivial closed two-sided ideals. And this happens exactly when the action is minimal and topologically free. Now, the class of nuclear C-star algebras is really quite big, even in the simple case. So we saw, for example, that hyperfinite factors in the 2-1 case, they're just the one. Well, this is not true for nuclear C-star algebras, even in the analog of the 2-1 case. We get way, way more C-star algebras, which makes things somewhat more complicated. So potentially we have a lot of cross products on our hands. Will they exhaust all nuclear C-star algebras? We don't know. But we would like to tell what kind of C-star algebras we get. Sorry, I have a rogue zero key that likes to randomly make zeros. Which is funny because I was making loads of mistakes with zeros. So many zeros ended up in these slides. But you know what I was not checking for? Hyperfine. I don't know why this comes up. Okay. I might get over it at some point. We'll see. So how can we tell what C-star algebras we get? Okay, so again, this is about identifying C-star algebras you might come across in the woods, in the jungle, whatever, in your lunchbox. I don't know. So we meet a C-star algebra and we might want to say, does this look like a C-star algebra we've encountered before? So what I'm really asking here is, can I find a C-star algebra B that I know and love, and are A and B isomorphic? So how do we determine an isomorphism of two C-star algebras? Is it even a reasonable question to ask if we can do this if we're just greeted with two C-star algebras? So this is really a classification problem now that I'm talking about. We have a class of mathematical objects. It might be quite complicated and ugly, and we would like to be able to determine isomorphism classes. So we need a complete set of invariants, and this should be neat and tidy. And it should be an isomorphism invariant. And we would like to show that maybe we can lift an isomorphism of the invariant back up to the original class of objects. And obviously the invariant's no good if the isomorphism problem is just as difficult down there. So we hope that at least this should be in principle somehow computable, and it should be easier to find isomorphisms in this case. And by complete set of invariants, I mean that these are actually in one-to-one correspondence. So every object in the set of invariants comes from some element in C. Okay, so it's much too much to expect satisfying classification of all C-star algebras. There's simply too many. If we want to get a result a Lacan, we want to restrict a little bit. So for example, we're going to stick to separable C-star algebras, so countable dense subset. We want to look at the simple ones because if we can't do those, we're not going to get very far. We want to look at nuclear C-star algebras because these are much more well-behaved. We have nice finite dimensional approximation properties we can use. And usually I'll stick to the unital case, although this is a little bit less important. Units make things easier though, so we'll do that. Okay, so let's move back to our approximately finite C-star algebras. Let's look for a Kohn type result. So we have UHF algebras, which are the inductive limits of matrices. These are somehow the simplest version of hyperfiniteness we might find in C-star algebra land. And as I mentioned, we also have AF algebras, which are inductive limits of finite sums of matrices. It's very easy to show that these are going to be separable and nuclear. Indeed, you can do this approximation via star homomorphisms. UHF algebras are always simple, but AF algebras aren't necessarily. And one of the very first classification results we saw in C-star algebra theory was the classification of UHF algebras. So these are classified by so-called supernatural numbers. What is that? This is an infinite product of primes to possibly infinite powers. So it's like a natural number, but of course, you can now take infinitely many primes. And to any UHF algebra, we can associate a supernatural number, which we can basically read off from this inductive system, which I've written down for you here. So this tells you what you want to put for KP as your power for your prime. And the point is that this is coming exactly from these the sizes of the matrix algebras that you're using and how they map into one another. Conversely, if you are given a supernatural number, you can construct a UHF algebra, and its inductive limit will give you back that supernatural number. So these, indeed, we have that two guys are isomorphic if and only if they have the same supernatural number. This was due to Glim. Moving on, what can we say about AF algebras? Well, Bradley showed that AF algebras can be classified by so-called Bradley diagrams. And I highlight this specifically in blue because it very well might come up in some talks on Cantor systems, whether in my talks or someone else's. Again, just highlighting, if you know a bit about this, the real strong links between operator algebras and topological dynamics. And then later, Elliott refined this classification of AF algebras to something called a dimension group, which is an ordered abelian group that one can associate to an AF algebra. This is slightly less complicated than writing down a whole Bradley diagram. And what this is, what this turns out to be is basically this ordered K0 group together with the class of the unit. And again, that probably doesn't make a lot of sense to people at the moment, but I will say more about that later on. In particular, it's basically coming from projections and C-star algebras. A projection just means an element that's self-adjoint and idempotent. It's exactly a projection as you would expect if you're thinking about an operator projecting onto a subspace. And then you say that their two projections are equivalent if you can find a partial isometry that moves one into the other, which is exactly what I've written here. This forms a nice equivalence relation on your projections, but that's not good enough. We actually want to look at projections over all matrix algebras. And then we take a Grothendieck group of these things, and this gives us K0. There's a way to put an order on it that's coming basically from the order structure on the C-star algebra, which comes from positivity. Again, this will become hopefully clearer later. Okay, but yeah, life is never so easy. This is still pretty far off from relating anything back to minimal dynamical systems like we had for hyperfiniteness in the von Neumann algebra setting. In particular, even if we have just a Z minimal system, so we have a single homeomorphism that's minimal acting on a space, then this cross product will be simple and separable and nuclear, but it's never going to be AF. It's never going to be UHF. It's never going to be AF. So these classification results simply do not apply. in this setting at all. Okay, so once Eliot classified his AF algebras by K-theory, he thought, maybe we can do this in much more generality. Maybe we can do something similar for our other version of hyperfiniteness, which is nuclearity. And so we conjectured that if you have two simple separable unital nuclear C-star algebras, and there exists an isomorphism between what I'll call the Eliot invariant, so I will say what this proposed invariant was in a moment, then there exists a star isomorphism of the C-star algebras, and moreover, it is exactly the star. It will always induce the map you had originally at the level of the invariant. So for AF algebras, this invariant turns out to be exactly this dimension group I mentioned. In more general terms, for unital C-star algebra, it's composed of the K-theory. So we just sort of vaguely saw what K0 was. There's also a K1 group in C-star algebras. Tracial states, in the case of a cross product, these are going to be the same as invariant measures in the dynamical system. And a map that pairs K0 with traces. So it's usually written as this sort of sextuple. Again, don't worry too much. The point is that we'd have an invariant. Okay, we have a potential invariant. It's potentially ish computable. Tracial states might be a problem, but okay. And yeah. So this was rather bold since basically only the AF algebras were done, but then similar techniques were used to classify other things coming from inductive limits that were a bit more general. So in particular, if we're worried about our cross products, then if this were to be true, it would at least cover these guys, because they're going to be when they're free and minimal and amenable, we get something that's simple, separable, nuclear. I just said this on the last slide, but again, the tracial states can again be read off directly from the action. But describing the K-theory in general is much trickier. There's no real good tools for this in full generality. For Z actions, we do have some nice tools available, and we'll see some more of those in subsequent talks. Okay, so what are some basic examples of what we might expect from the invariant? So let's take the most easiest C-star algebra we can, which is both finite dimensional and simple, the complex numbers. So for this, we just get in K-theory, Z, what? This should, sorry, Z, the order structure is given by the positive cone of Z, which is the natural numbers. The unit is just 1. K1 is 0. There's a single tracial state, and the pairing is more or less degenerate. If we instead look at matrices over the complex numbers, we get exactly the same thing, except for now the trace this is just the usual matrix trace, which is not normalized in this setting. And instead of 1 for the class of the unit, we get the size of the matrix algebras. So we see that this is able to distinguish between the complex numbers and matrices. But you might ask, can we find other C-star algebras that do have these invariants and might be still simple, nuclear, etc.? Okay, and so this was a sort of a major stumbling block for Eliot's classification in some sense, because there was a question, can you find a simple unital nuclear C-star algebra that's infinite dimensional and has unique trace? Okay, so this is what this is saying is it's now an infinite dimensional guy that looks from the invariant's point of view exactly like the complex numbers. Okay, so complex numbers are obviously not infinite dimensional. So this suggests that maybe some refinements are needed. If this were to be true, and indeed in this paper, they did construct such a C-star algebra. It's usually denoted by curly Z, and we call it the Jiangsu algebra. after the creators. Oh, there's a stray zero there. Okay, so immediately you say, okay, well, let's just say that we demand everything be infinite dimensional because, okay, you know, if we see C or MN or something, whatever, that's easy enough to figure out. But this actually causes problems even in the infinite dimensional case. So this Jiangsu algebra has even further implications. So if we have a simple separable unital nuclear C-star algebra, then it turns out that this Elliott invariant behaves relatively well with respect to tensor products. So just as you might think, tensoring by C doesn't do anything, at the level of the invariant, we tensor by Z, nothing happens. These will have the same Elliott invariant in all these cases with a little caveat here on the order structure. So if the conjecture were to be true, then we would always have that A is isomorphic to itself tensored with this Jiangsu algebra. And this turns out to not be true. In addition to infinite dimensionality, or well, actually, I guess instead, we ask that this holds. So we ask that A is isomorphic to A tensor Z, and we call such a C-star algebra Z stable. Okay, so after many years, this conjecture actually turned out to be almost true, which is really quite amazing. Stupid zero key. And here's the refined version. So now we have just added Z stability. So they have to be isomorphic to themselves tensor with Z, and something called the universal coefficients theorem. And then we get the exact statement. So I told you what Z stability is. The coefficient theorem is, loosely speaking, just something that allows you to use K-theory as a good invariant. Okay, this is going to drive me nuts. No. Okay. It holds for all known nuclear C-star algebras. In particular, will hold for anything in this talk, but it's still an open question whether or not nuclearity actually implies the UCT. But as I said, you can essentially ignore this because it will be automatic in all the constructions we see. Okay, so back to cross products. Where do they fit in? Can the Elliott invariant tell us anything about the underlying dynamics? So when we had a countable discrete amenable group acting on a measure space in a probability, ergodic and essentially free, then this was the hyperfinite 2-1 factor. And this then allows us to conclude orbit equivalence of the underlying dynamics, or even the Borel equivalence relations. So now if we want to apply such a theorem in C-star land, we also need to determine whether our cross products are Z stable. And even for cross products by Z, this turns out not to hold in full generality. But nevertheless, there are many cases where things work quite well. And in particular, if we're talking about cross products, things work exceptionally well when our space X is zero dimensional. Infinite and zero dimensional, in particular, is a Cantor set. So things work very well for Cantor minimal systems. There, the Elliott invariant looks just like the invariant for a simple AF algebra, so it's a dimension group. But now we have a non-trivial K1. So it turns out that one can actually say something about the dynamics from this Elliott invariant. Oh, I should have mentioned also there's a single tracial state. No, that's not true. It can any simplex of tracial states. So I should have said, again, the tracial states come from invariant measures, and that can be pretty wild. But nevertheless, this can be used to classify orbit equivalence of the Cantor minimal systems. Hopefully, we'll see some of this at some point. Right. So Bradley diagrams also, which we saw were used to classify AF algebras originally, these also have become very important tools in Cantor dynamics. So there's a way of associating a Bradley diagram to every Cantor minimal system. And in fact, this Bradley diagram, if you ignore the action that you add to it, this will give you exactly the AF algebra whose dimension group is the dimension group of this K0 group of the Cantor minimal system. So they're very, very intimately related. So I've been talking mostly about minimal systems, but another zero-dimensional class of systems that can also be captured very nicely by C-star algebras are shifts of finite type. So here, these are far from being minimal in general, so the cross-product construction is not what we want, because we ultimately would prefer to have things that are simple or close to being simple. But it turns out that we can do nice models of shifts of finite type by either AF algebras or something called Kunz-Krieger algebras. And once again, the associated C-star algebraic invariant gives us information about the dynamics in a very, very nice way. So the upshot is that zero-dimensional spaces, they behave a lot more like the von Neumann setting, with substantially more intricacies. Nevertheless, a lot of the von Neumann stuff can be brought across in a reasonable way. Now, so what's going to come up, hopefully in my lectures, time permitting, later on in the next two lectures, we can actually unify these two pictures of the cross product and the C-star algebras that we're going to build from shifts of finite type by something called a topological groupoid. So you model these first as groupoids, and then we construct a C-star algebra out of the groupoid. And these have a very nice dynamical flavor in general. And yeah, they also have a sort of reconstruction Kleinfeld-Weiss type theorem that we'll hopefully see. So after looking specifically at these zero-dimensional systems, we want to see what happens when we can then allow X to be positive dimension. There, things become a lot more complicated, and we don't get the precise back and forth that we do in the zero-dimensional case. So we might ask what the cross product can remember, and with the Elliott invariant in mind, we might also ask ourselves, what can it actually look like? So we know that, for example, in the von Neumann case, we get all the hyperfinite 2-1 factors. There's only one. Do we get all possible Elliott invariants from cross products? Don't know. For the shifts of finite type, we're going to generalize to Smale spaces, which are a nice set of hyperbolic dynamical systems. And we can construct several C-star algebras out of these. And again, we will see that we can ask basically the exact same questions. What is reflected in the C-star algebra that's coming from the Smale space? And how much do we remember? Okay, so I will end there. Thank you very much. And maybe just before we have questions, I wanted to say that I want to dedicate my talk to Shigato, who died very recently. He was a postdoc at IMPAN for a while, fellow operator algebraist. So just wanted to say that. All right, so I'll go back to this slide.